I made a video recently about the speed of light, and it got me thinking what would happen if we were able to travel at speeds close to the speed of light. In today's video, I'm going to talk about what happens. So I'm going to talk about time dilation, and I'll also mention length contraction as well. Let's find out more. So let's begin with what time dilation is. If one observer is moving at a significant fraction of the speed of light relative to another observer that's stationary, the observer that's moving very quickly will experience time passing more slowly from the point of view of the stationary observer. But why? So first of all, in this video I'm going to talk about clocks, but this isn't really to do with clocks. This is time itself. It isn't just that clocks run more slowly. Time itself runs more slowly. It's just that we measure time using clocks. So that's important point number one. Also, I need to be very careful about the language here. If I'm the person traveling very quickly in a spaceship, I experience time passing normally. I don't experience the time passing more slowly. However, to an observer that's stationary outside of my spaceship, they will see time passing more slowly for me. Important point two is that time dilation is a feature of both special relativity and general relativity. But the general relativity version of time dilation is due to gravity, so I'm not going to deal with that here, maybe a future video. Time dilation comes down to one key idea, and that is that the speed of light is the same for all observers no matter what their speed is. This means that if I'm traveling at half the speed of light and shown a torch ahead of me, the light will still travel away from me at the speed of light. So how does this cause time dilation? Well, let's conduct a little thought experiment. Imagine I have a box. It could be a spaceship, but for simplicity's sake, I'm going to call it a box. And inside this box is a person, and let's ignore gravity, etc. And this person is throwing a ball and it's bouncing off the roof and coming back to the person. This here is the equation that links distance, velocity, and time. And if we rearrange it, it will tell us how to calculate the time taken for the ball to hit the roof. Now I'm going to put a person outside the box to make the same measurements of the time taken. So currently these people agree on the distance traveled by the ball, the velocity of the ball, and the time taken. And now I'm going to start the box moving in this direction. As far as the person inside the box is concerned, the ball is still just moving up and down. So to them, nothing has changed. However, to the person outside the box looking in, the ball will be traveling further because it's not just moving up and down, but it's also moving horizontally. So this value has increased, but the ball is also traveling faster because it isn't just moving up and down, it's also moving horizontally. So this value here will also have increased. So the people inside and outside the box will now disagree on the speed of the ball and the distance the ball has traveled, but will still agree on the amount of time taken for one bounce. Now inside the box, I'm going to place a clock and it works by light. Here is my box again, and I'm going to say that the height of the box now is L. The clock works by emitting a photon of light from the floor of the box. This photon flies from the floor and is detected by a detector in the roof of the box, and that I'm going to call one tick of my clock. And I can work out how long one tick takes. So here I'm going to write how long one tick takes. I'm going to call this value Ti because this is the length of time taken for one tick measured by a person inside the box, which is stationary. Even if the box is moving relative to the box, any measurement taken inside the box is still stationary. I hope that made sense. One tick of the clock then is the time taken for the photon of light to travel up to the roof. So this distance L. Here's the equation that links time, distance, and speed or velocity again. So the time taken for the photon of light to travel this distance is L(c), the speed of light. And as I've already said, I'm going to call this Ti. And now I'm going to start the box moving in a straight line in this direction. And the box is going to move with the velocity that I'm going to call v. I've still got my person inside and outside the box to take the measurements. Now, I'll sort out the maths in a little bit, but I just want to get the concept first. If you see the person outside the box sees the photon move slightly differently. They see the photon trace a longer path. They see the photon start here and trace a path up to this point. And essentially what I need to find is the time taken for a person standing outside the box to measure the time for one tick of this clock. In other words, the amount of time taken for the light to trace this path. But don't forget, this is a photon of light and the two people must agree on the speed of light. They must agree on the speed of that photon. So in order for the photon of light to travel a greater distance, there's got to be more time for it to do so. That means to the observer outside, the clock inside the box must be running more slowly to allow more time for the light to have traveled a greater distance, because don't forget the two people must agree on the speed of light. And also, even though again I'm talking about the clocks, it's the passage of time that's slower. Okay, so let's do the maths. And this actually allows us to calculate how much more slowly the clock is running. I've looked at a number of derivations of this, and no one seems to use a consistent approach. So I'm going to use letters in the equations that make sense to me, and I hope they make sense to you too. So let's work out how much the time dilation is affecting the person in the moving box. Here's my moving box again, and the value I want to find, I'm going to call 2. This is the time measurement made by a person outside the box, measuring the time taken for the clock to tick in the moving box. Hence, 2 I'm going to call the distance the light path appears to move to be d, and so to d over c. So now I need to work out how far the distance d is. Okay, so there's a bit more I can fill in here. This distance here from our equation, distance is velocity times time. So this length is velocity, which we've called v multiplied by time, which is 2o. And this now makes a triangle, and triangles are great. So let's put a line here. And we know that this distance is L. And now we have a right angle triangle. So using Pythagoras' theorem, we can now find d because d2 is equal to L circumflex 2 plus v2. This means that d is the square root of v2 plus L2. We know that time is distance over velocity. So 2 is distance d, which we know is equal to the square root of v2o squared plus L circumflex 2, divided by the velocity, which we know to be c because it's a photon of light that's moving and it's always moving at c. We also know that from this equation, distance equals velocity time. So then we know that L is cti, so we can substitute this into our value for L here in this equation. This means that 2 equals the square of v to o all squared plus cti all squared c. Well, let's get rid of this square root. And I can do that by squaring everything. So to circumflex 2 e cube u equals sine vt to o all 2 plus ct I all circumflex 2 c circumflex 2. Let's now get rid of these brackets. So to circumflex 2 equals sine v circumflex 2 2 c circumflex 2 plus c circumflex 2 t, I circumflex 2 c circumflex 2. And I can cancel these c circumflex sq, and that gives us v circumflex 2 to o circumflex 2 c circumflex 2 plus t I circumflex 2. Now let's put all of our terms on the same side of the equation. This gives us to O2 minus v circumflex 2 to circumflex 2, c circumflex 2 e cube u equals sine ti circumflex 2. Now I have a common factor in these two terms, which is 2o squared. So I can simplify this side of the equation to o squared open brackets 1, v circumflex 2, c circumflex 2 e cube u equals sine ti squared. I can now take this term and divide both sides by it. And this gives us to o circumflex 2 equals sine ti squared. 1 use v circumflex 2, c2. And finally, taking the square root of both sides, it gives us to o, that's the value we want, equals t, the square of 1 us v circumflex 2, c circumflex 2. Okay, and I hope you followed along with that. Okay, so I can now take the ti out of this to give us 2 is equal to ti multiplied by this here. And this stuff here is called the Laurent factor, or gamma. So as long as I know the time recorded by a stationary observer and the velocity of the moving object, I can calculate the amount of time dilation. So let's try an example or two. For an object moving at 50% of the speed of light, the calculation gives us a value of 1.16 roughly. This means that a person observing the moving object would experience an hour, but they would see the moving object only experience a little over 52 minutes. For an object traveling at 99% the speed of light, this gives us a value of about 7.0909. So the hour that the stationary person spends observing the moving object, they see the passage of only 8 and 12 minutes for the moving object. In addition to people disagreeing on the time because of this equation, they'll also disagree on the distance. And this leads to what's known as length contraction. Distances in the direction of travel will be shortened. And since the length of an object is just the distance between the front and the back, this is going to cause length contraction. And the equation for working this out involves our Laurent factor that we've used before. So do we have any proof for this? Well, actually we've got quite a lot of proof. We've observed particles called muons. These are created in the upper atmosphere by the collision of cosmic rays with particles in the atmosphere. These muons are also traveling at speeds close to the speed of light. And muons are really short-lived particles existing for only a tiny fraction of a second. However, due to their speeds, we've observed muons existing for much longer than they should do because of their incredible speeds and time dilation. We've also used incredibly accurate clocks that were synchronized. We've then flown one of them around the world as fast as we could. And even at these speeds, which are a tiny fraction of the speed of light, the time difference in the clocks was as expected in relation to time dilation. Also, our GPS satellites have to have built into their software factors that account for time dilation, allowing them to accurately position objects on the Earth. So, this brings us back to our stationary life back here on Earth. I will be delving into the speed of light a bit more in the future, but for now and until next time, thank you for watching.